Hello and welcome back. Let me open tonight with something about a picture you've seen 1,000 times. Think of a diagram of the solar system, the sort on a classroom wall, or the back of a cereal box. The Sun on one side, then Mercury, Venus, Earth, Mars, the asteroid belt, then the big ones, Jupiter, Saturn, Uranus, Neptune, perhaps Pluto, depending on the vintage. And then the edge of the page. Here's the thing about that picture. It isn't wrong in its details. It's wrong in where it stops, and by an amount that's genuinely difficult to hold in your head. Neptune sits about 30 times further from the Sun than we do. Light takes 4 hours to reach it. That's the outer edge of the familiar map. But the Sun's gravitational domain, the region where its pull dominates over the pull of neighboring stars, extends outward for something like 100,000 times the Earth's distance, perhaps 200,000. Nearly 2 light years in every direction. So if you drew the Sun's actual realm as a football pitch, everything on that classroom diagram, all 8 planets, the asteroid belt, Pluto, the lot, would fit inside a circle a few millimeters across, right at the center spot. The rest of the pitch would be blank and essentially unexplored, and it's where tonight's question lies. Because in all that room, something the size of Neptune could be sitting quietly, and we would very likely not have noticed. It would be too faint for most surveys, and moving so slowly across the sky that it would look like a fixed star. And there is real evidence, contested, argued over, not settled, that something out there is nudging the things we can see. Let's spend a chapter on that scale, because everything tonight depends on it. Astronomers measure distances in the solar system using the astronomical unit, the distance from the Earth to the Sun, about 150 million kilometers. Light crosses it in 8 minutes. On that scale, Jupiter is at 5, Saturn at 9.5, Uranus at 19, Neptune at 30. Then the Kuiper belt, a broad ring of icy bodies from about 30 to 50. Pluto is in it, averaging about 39. Beyond that, the scattered disk, objects on elongated orbits reaching out to a few hundred. And then further still, the Oort cloud, a vast spherical shell of comets, thought to extend from a few thousand out to perhaps 100,000 astronomical units. That's the region long-period comets fall in from, and no object has ever been directly observed there. Its outer boundary is roughly where the Sun's gravity gives way to the general gravitational field of the galaxy, about 1.5 to 2 light years. So the familiar planets occupy the innermost 0.03% of the Sun's territory. Everything else is dark, cold, and almost entirely unmapped. Before we go looking for something hidden, let's take stock of what has actually been found beyond Neptune, because the story is fairly recent. For most of the 20th century, the answer was Pluto, discovered in 1930, and nothing else. Then, in 1992, after years of patient searching, an object was found orbiting beyond Neptune, a faint body a few hundred kilometers across. And once one was found, others followed quickly. Today, there are thousands catalogued. They're collectively called trans-Neptunian objects, and they fall into several populations. The classical Kuiper belt objects orbit in the ring between about 40 and 50 astronomical units on fairly circular paths. Then there are objects in resonance with Neptune, orbiting in step with it, protected from close encounters by the timing. Pluto is one of these, going round twice for every 3 of Neptune's orbits. And then the scattered disk, objects on elongated, tilted orbits, thought to have been flung outward by encounters with Neptune long ago, reaching out to hundreds of astronomical units at their furthest. Those 3 populations are reasonably well understood. And then there's a fourth, which isn't. In November 2003, a survey found something unusual, and it opened the whole question. It was a reddish object, perhaps 1,000 kilometers across, and its orbit was unlike anything known. At its closest approach to the Sun, it comes no nearer than about 76 astronomical units, more than twice Neptune's distance. At its furthest, it goes out to around 900. A single orbit takes something like 11,000 years. It was named Sedna, after an Inuit goddess of the sea, on the grounds that it inhabits a very cold and very distant ocean. And the problem is its closest approach. 76 astronomical units is far too distant for Neptune to have put it there. Neptune's gravitational influence simply doesn't reach that far. An object scattered outward by Neptune would come back into around 30-something at its closest, not 76. So Sedna is detached, decoupled from the known planets, on an orbit that nothing in the current solar system can explain. Something must have lifted its closest approach away from Neptune's reach. And whatever did it either isn't there anymore, or hasn't been found. For a decade, Sedna was a single peculiar object, and single objects are easy to set aside as flukes. Then, in 2014, Chad Trujillo and Scott Shepard announced a second one, a body given the designation 2012 VP-113, and nicknamed Biden by its discoverers because of the initials. It's smaller than Sedna, perhaps 500 kilometers across, and its closest approach is about 80 astronomical units. Its furthest is around 450. Two objects, both detached, both with closest approaches far beyond Neptune's reach. And in the paper announcing it, Trujillo and Shepard pointed out something else. They looked at all the known objects with distant orbits, and noticed that a particular orbital angle, the argument of perihelion, which describes where in its tilted orbit an object makes its closest approach, seemed to cluster around similar values. That shouldn't happen. Those angles should drift and randomize over billions of years. Finding them clustered suggests something is currently maintaining the alignment. They suggested a possible cause, an unseen planet of perhaps a few Earth masses, somewhere out beyond 250 astronomical units, shepherding those orbits. The idea was noticed, and it was taken up 2 years later by two astronomers at Caltech, one of whom had spent a decade being skeptical of exactly this sort of claim. The two Caltech astronomers were Konstantin Batygin and Michael Brown, and their partnership is part of what makes this story interesting. Brown is an observer who has spent much of his career finding distant objects, including the one whose discovery led to Pluto's reclassification. He had a reputation for skepticism about claimed planets beyond Neptune, having seen several such claims come and go. Batygin is a theorist, considerably younger, who works on the dynamics of planetary systems. They set out, by their own account, to disprove the Trujillo and Shepard suggestion. Brown expected to show that the clustering was a selection effect, an artifact of where telescopes happened to have looked, and Batygin expected to show that no plausible planet could produce it. Instead, working through the dynamics carefully, they found that a distant planet could produce the observed pattern, and that it could produce several other features of the outer solar system at the same time. They published in early 2016 in a paper that proposed a planet of 5 to 10 Earth masses on a highly elongated orbit averaging several hundred astronomical units from the Sun. And unlike previous claims, this one came with detailed dynamical modeling and specific predictions, which is why it was taken seriously in a way that earlier proposals had not been. Let's spend a chapter on the evidence itself, because it's more specific than some orbits look similar. Consider the most distant known objects, those whose orbits stay well beyond Neptune's influence, so their paths aren't being scrambled by the known planets. Each such orbit is a long ellipse, tilted at some angle to the plane of the solar system, and oriented in some direction. 3 angles describe that orientation. If nothing were organizing them, those angles should be random. Over 4.5 billion years, any initial alignment would have drifted apart, because each orbit precesses at a slightly different rate. What Batygin and Brown reported was that the handful of most distant objects known at the time had orbits that were physically aligned, their long axes pointing in roughly the same direction in space, and their orbital planes tilted in a similar way. The chance of that happening randomly, they calculated, was small, well under 1%. And a planet on a similarly elongated orbit, oriented in the opposite direction, could maintain that alignment through a resonant gravitational interaction, shepherding the distant objects into a common configuration over billions of years. That's the core argument. Not an unexplained wobble, but a pattern in the orientations of a small number of very distant orbits. What strengthened the case was that the same hypothetical planet appeared to explain several other things that hadn't been designed into the model. The first was a population of objects on orbits tilted almost perpendicular to the plane of the solar system, nearly at right angles, which is a strange place to be. The simulations produced exactly such objects as a natural consequence, and a handful had already been observed. The second was the existence of the detached objects like Sedna, whose closest approaches are lifted beyond Neptune's reach. A distant planet would do that. The third was the tilt of the Sun itself. The Sun's rotation axis is inclined about 6 degrees relative to the plane the planets orbit in, which has never had a satisfying explanation. A massive distant planet on a tilted orbit would, over billions of years, gradually tip the plane of the inner planets relative to the Sun, producing roughly that amount. The fourth involved objects orbiting the Sun backwards, which also emerged from the simulations. Whether all of those hold up is part of the ongoing argument, but the pattern, a single hypothesis explaining several unrelated oddities that it wasn't constructed to address, is the kind of thing that makes theorists pay attention. That's how a proposal moves from speculation to something worth spending telescope time on. Let's describe the hypothetical object, because the picture is quite specific. The mass estimates have varied as the modeling improved. The original paper suggested 10 Earth masses. Later refinements brought it down, with recent versions favoring something around 5 to 7. That would make it a super-Earth or a mini-Neptune, larger than our planet, considerably smaller than Neptune, and almost certainly with a substantial atmosphere of hydrogen and helium over an icy or rocky interior. Its orbit would be elongated. Estimates for the average distance have ranged from around 400 to 600 astronomical units, with the closest approach perhaps 200 to 300 and a furthest point well beyond 1,000. A single orbit would take something like 10 to 20,000 years. If it has been there since the solar system formed, it has completed perhaps 300,000 circuits. Its surface temperature would be extraordinarily low, a few tens of degrees above absolute zero, warmed almost entirely by whatever internal heat it retains rather than by sunlight. From its surface, the Sun would be a very bright star. Bright enough to cast a shadow perhaps, but no more than a point of light, hundreds of times fainter than a full moon here, and utterly incapable of warming anything. The obvious question is how something that large could hide, and the answer comes down to two numbers. The first is brightness. Objects out there shine only by reflecting sunlight, and the amount of sunlight falling on them drops with the square of distance. Then the reflected light drops again with the square of distance on its way back to us. So the apparent brightness falls off as the fourth power of distance. Double the distance and it becomes 16 times fainter. At 500 astronomical units rather than 30, an object is roughly 75,000 times fainter than it would be at Neptune's distance. The estimates put a planet like this somewhere around magnitude 22 to 25, faint enough that only large telescopes can detect it, and only in careful deep exposures. The second number is motion. Detecting a distant solar system object usually means finding something that moves against the background stars between images. At 500 astronomical units, orbital speed is very slow, and the apparent motion is dominated by the Earth's own orbit. The object would shift by only a small amount over months, enough to detect, but easily missed by surveys not designed for it. And there's a third factor: where to look. The proposed orbit is elongated, and the object is most likely near its furthest point. Since it moves slowest there and spends most of its time there, that region covers a substantial area of sky, and part of it lies toward the crowded band of the Milky Way, where faint objects are lost among stars. A great deal of searching has been done, and it's worth a chapter on what's been ruled out. The first constraints came from infrared surveys. A satellite that mapped the whole sky in infrared in 2010 would have detected a planet of Saturn's mass out to about 10,000 astronomical units, and a Jupiter mass object out to 26,000. So the large possibilities are eliminated. There is no Jupiter or Saturn hiding in the outer solar system. Whatever might be there is small enough to have escaped that survey, which is consistent with the 5 to 10 Earth mass proposal, since such an object would be far too cool and faint for that instrument. Since then, deep optical searches have covered substantial parts of the predicted region. Brown and Batygin have used large telescopes to search systematically, and have reported covering a majority of the plausible sky area without a detection. Other groups have searched independently, using survey data and dedicated observations. There's also a citizen science project that enlists volunteers to examine infrared images for faint moving objects, which has found brown dwarfs and other faint neighbors, though nothing matching the prediction. And in 2025, a candidate was reported from archival infrared data taken decades apart. The Planet 9 proponents themselves noted that the implied orbit would be inconsistent with what their model requires. So if it turns out to be real, it would be something else entirely, which would be interesting in its own way. Now let's give the skeptics their chapter, because the objection is serious and it may well be right. The central concern is observational bias. The clustering was identified in a small number of objects, originally 6, later a few more, discovered by different surveys, using different telescopes, pointed at different parts of the sky at different times of year. And surveys don't cover the sky evenly. They observe when the weather is good, when the moon is down, and where the telescope can point. Those preferences can create apparent patterns in the discovered population that reflect the observing schedule rather than the objects themselves. If you only look in certain directions, you'll only find objects whose orbits bring them into those directions, and that could produce apparent alignment where none exists. The most careful test of this came from a survey designed from the start with a fully characterized observing pattern, meaning that for any hypothetical population, you can calculate exactly what fraction that survey would have found. That survey, run from Hawaii over several years, found a number of distant objects, and when its team analyzed their own sample, accounting for their known biases, they concluded that the orientations were consistent with being random. Their sample was small, and the authors were careful about that. But it was the first analysis where the selection effects were genuinely under control. That result didn't settle things, and the exchange since has been vigorous and largely constructive. The proponents responded that the bias-controlled survey sample was too small to be decisive, and that combining it with other data still favors clustering. They've since published analyses attempting to model the selection functions of all the major surveys together, and report that the signal survives. The skeptics respond that modeling other people's selection functions retrospectively is extremely difficult, and that the significance claimed depends heavily on choices made in that modeling. Several independent groups have examined the data with different methods and reached different conclusions. Some find the clustering significant, others find it consistent with chance. There's also a debate about which objects should be included. Different cuts on orbital distance and eccentricity change the sample, and therefore the result, which is exactly the situation where a genuine signal and a spurious one are hardest to distinguish. The honest summary is that this is an unresolved statistical dispute among competent people, turning on how well a small sample selection biases can be characterized after the fact. Which is not a satisfying answer, but it's the true one. And it's why the question will be settled by finding the object, or by a survey large enough to make the statistics unambiguous, rather than by further argument. There's an alternative that keeps the dynamics without the planet, and it deserves a chapter. The idea is that instead of one massive object, the alignment could be produced by the combined gravity of a large number of small ones, a massive disk of debris in the outer solar system, totaling perhaps a few to 10 Earth masses spread across a broad ring. Such a disk, if it existed, would exert a collective gravitational influence on the distant objects. and simulations have shown it can produce clustering of the kind observed. It has an appeal. It requires no undiscovered planet, only undiscovered small bodies, which are far easier to hide. The difficulty is that the required mass is substantial. Current estimates of the total mass in the outer solar system are far lower than the models need, perhaps 1/100th of an Earth mass in the known Kuiper belt. Finding 100 times more in a region we've partly surveyed is not straightforward. There are also questions about whether such a disk would be stable over billions of years, and whether it should have been detected by its collective effect on other things. So it's a live alternative, taken seriously with its own problems. And notably, it would still mean something substantial is out there, just distributed rather than concentrated. A more radical alternative has been proposed, and it's worth a chapter for completeness. Some researchers have examined whether modified theories of gravity, of the kind proposed to explain galaxy rotation without dark matter, could produce the observed orbital alignments in the outer solar system. The idea is that at very large distances from the Sun, where accelerations become extremely small, gravity might behave slightly differently from Newton's prediction, and that could organize distant orbits. Papers have been published arguing that such a model reproduces the clustering without any additional mass. The objection is substantial. Modified gravity theories are already constrained by observations within the solar system, and by galaxy dynamics, and by cosmology. Making one work for distant Kuiper belt objects without breaking anything else is demanding. Most of the field regards it as unlikely, and it hasn't gained wide traction. But it illustrates something worth noting. An unexplained pattern in the orbits of distant objects is in principle an anomaly that could have several causes, and a new planet is only the most conservative of them. There's one more proposal, and it's the one that gets the most attention, so let's handle it carefully. In 2019, two researchers pointed out that the gravitational evidence, if it's real, constrains only mass and orbit, not composition. A 5 Earth mass object could be a planet, or it could be something far smaller and denser. Specifically, it could be a primordial black hole, one formed in the first instance after the beginning, rather than from a collapsing star of a mass in that range. Such an object would be tiny. A black hole of 5 Earth masses would have a horizon about the size of a grapefruit. It would reflect no light and emit essentially nothing detectable at that distance, which would explain why searches have found nothing. It's not a crazy suggestion. Primordial black holes are a legitimate hypothesis, proposed for other reasons, and a candidate for dark matter, though the possible mass ranges have been steadily squeezed. The proposed test is interesting. Such an object, moving through the outer solar system, would occasionally encounter small comets, which would be torn apart and produce brief flares of radiation as material fell in. Surveys watching the whole sky repeatedly might catch such events. Nothing has been found, and the probability of a primordial black hole of exactly the right mass happening to be captured into a solar orbit is, most researchers judge, very low. But it's a legitimate possibility, and it makes the point that the evidence constrains gravity, not appearance. Suppose it exists. Where does a planet on a 500 astronomical unit orbit come from? There are 3 main answers, and none is comfortable. The first is that it formed there. That's difficult because the disk of material from which planets formed was far denser near the Sun and extremely thin at those distances. Building a several Earth mass object from such sparse material in the time available is not something the standard models produce. The second, and most favored, is that it formed much closer in, among the giant planets in the crowded early solar system, and was then flung outward by a gravitational encounter with Jupiter or Saturn. That happens readily in simulations. Early planetary systems are chaotic, and objects get scattered. The problem is that a scattered object usually leaves entirely, or comes back into where it started. To end up on a stable distant orbit, something must lift its closest approach, and the most likely candidate is a passing star early in the Sun's life, when the Sun was still in the cluster where it formed. The third possibility is capture. The planet formed around another star, was ejected from that system and was later caught by ours during a close encounter in the Birth cluster. That's a low probability event for any individual system, but with many stars in a cluster and many free-floating planets, it isn't impossible. There's a broader argument for why a planet like this wouldn't be surprising, and it comes from other star systems. Since the 1990s, thousands of planets have been found around other stars, and one of the clearest results is the abundance of a particular size class. Planets between the Earth and Neptune in size, super-Earths and mini-Neptunes. They appear to be the most common type of planet in the galaxy. Something like a third to a half of Sun-like stars seem to have one. And our solar system has none. There's nothing between Earth's size and Neptune's, a gap in the sequence that is, on the galactic evidence, unusual. Which raises the possibility that we do have one, and it's simply somewhere we haven't looked. That's not evidence, and it should be stated carefully. Selection effects in exoplanet surveys favor close-in planets, and our system's architecture may well be genuinely unusual for other reasons. But it does mean that a 5 Earth-mass planet is not an exotic thing to propose. It's the most common kind of planet we know of, and its absence here is arguably the thing requiring explanation. There's a precedent for finding a planet by its gravity alone, and it's one of the great triumphs of theoretical physics. Let's take it slowly. Uranus was discovered in 1781 by William Herschel, who initially took it for a comet. Once its orbit was calculated, astronomers began tracking it carefully. And it misbehaved. Over the following decades, its observed position drifted away from where Newton's laws predicted it should be, by amounts far too large to be measurement error. Two mathematicians independently took up the problem, Urbain Le Verrier in France and John Couch Adams in England. Both assumed the laws were correct and something unseen was tugging on Uranus, and both calculated where that something must be. Le Verrier sent his prediction to the Berlin Observatory in September 1846. The astronomer there, Johann Galle, and his assistant looked that night and found an object within 1 degree of the predicted position on the first evening of searching. It was Neptune, a planet found by calculation, then confirmed by pointing a telescope at the coordinates. That result is often described as the greatest vindication of Newtonian mechanics, and it established the method: measure an anomaly, infer the mass causing it, go and look. Le Verrier, encouraged, applied the same method to a second anomaly, and this time it failed instructively. Mercury's orbit also misbehaves. The point of its closest approach to the Sun creeps around slightly with each circuit, a precession which is expected from the pull of the other planets. But the observed rate exceeded the predicted one by a small amount, about 43 arcseconds per century. Le Verrier concluded there must be another planet, closer to the Sun than Mercury, whose gravity accounted for the excess. He named it Vulcan, and the search began. There were reported sightings by respectable observers. Expeditions were mounted during solar eclipses, when an object near the Sun might briefly be visible. Amateur astronomers claimed detections. None held up. Vulcan does not exist. There is nothing there. The anomaly was real, precisely measured, and correctly identified as a problem. But the cause wasn't a missing object. In 1915, Einstein's general relativity produced Mercury's extra precession exactly, with no adjustable parameters, and it was the first great confirmation of the new theory. So the same method, applied by the same brilliant man to two similar-looking anomalies, gave one triumphant discovery and one ghost. That pairing is the reason nobody in this field speaks with certainty, and it's worth a chapter. When you observe an anomaly, there are two broad explanations. Something is there that you haven't seen, or your understanding of the physics is incomplete. Neptune was the first case, Vulcan was the second, and from the anomaly alone, there's no way to tell which kind you have. For Planet 9, there's a third possibility that neither of those cases had, that the anomaly isn't real at all, that the clustering is an artifact of how the sample was collected. So there are three doors, and the current evidence doesn't clearly distinguish them. What makes the Planet 9 case more like Neptune than like Vulcan is that the proposed explanation is entirely ordinary. A 5 Earth-mass planet on a distant orbit requires no new physics whatsoever, and such planets are common around other stars. What makes it less like Neptune is the quality of the data. Leverrier had decades of precise positional measurements of a bright planet. This rests on the orbital orientations of a few dozen faint objects, discovered by surveys with poorly characterized biases. That's the honest comparison, and it's why the field is divided. There's a third historical case, and it's the closest analog, and it ended strangely. In the early 20th century, some astronomers believed there were residual discrepancies in the orbits of Uranus and Neptune, even after accounting for all known planets. Percival Lowell, the wealthy American who built an observatory in Arizona and famously believed in canals on Mars, took up the problem. He calculated the properties of a further planet, which he called Planet X, and searched for it for years until his death in 1916. The search resumed in 1929, when a young man named Clyde Tombaugh was hired to photograph the sky systematically and compare plates. In February 1930, comparing two plates taken weeks apart, he found an object that had moved. It was announced as the 9th planet and named Pluto. For decades, that was regarded as a vindication of Lowell's prediction, and it wasn't. Pluto is far too small to have caused any perturbation of Uranus or Neptune. Its mass estimate fell steadily over the following decades as measurements improved, from roughly the Earth's mass down to about a 500th of it. Worse, the residuals Lowell was trying to explain turned out not to exist. When a spacecraft flew past Neptune in 1989 and provided an accurate mass, the discrepancies vanished entirely. So the prediction was based on an error, and the discovery was a coincidence, a genuine object found in roughly the right part of the sky by a very thorough search. There have been other proposals for distant companions, and two are worth a chapter because they illustrate how such ideas rise and fall. In 1984, two groups independently suggested that the Sun might have a distant companion star, a faint dwarf on a highly elongated orbit, taking around 26 million years. The motivation was a reported periodicity in mass extinctions in the fossil record. The idea was that the companion, at its closest approach, would disturb the Oort cloud and send a shower of comets into the inner solar system. It was named Nemesis, and it caught the public imagination immediately. The evidence has not held up. The claimed periodicity in extinctions is disputed and depends heavily on how the record is analyzed, and infrared surveys have now covered the whole sky deeply enough to exclude any stellar companion out to enormous distances. There is no dim star orbiting the Sun. A related proposal, called Taish, suggested a Jupiter-mass planet in the inner Oort cloud, based on claimed patterns in the orbits of long-period comets. That's also been excluded by the same infrared surveys, which would easily have detected an object of that mass. So two proposed distant companions have been ruled out definitively, which is itself a useful result, and part of why the current proposal is pitched at a mass small enough to have escaped those searches. There's a constraint from an unexpected direction, and it's rather elegant. For over a decade, a spacecraft orbited Saturn, and its distance from Earth was measured extremely precisely by timing radio signals to within tens of meters. That gives an exquisitely accurate measurement of Saturn's orbit, and any unmodeled gravitational influence from an undiscovered massive object would show up as a discrepancy. Analyses of that data have been used to constrain where a distant planet could be. Certain regions of the possible orbit are disfavored, because a planet there would produce a measurable effect on Saturn's motion that isn't seen. The constraints aren't decisive. They depend on assumptions about the planet's mass and current position, and the most likely locations are far enough away that the effect would be below the measurement threshold. But they've been useful for narrowing the search, and they eliminate the closer end of the proposed range. There have also been attempts to use the timing of pulsars, those extraordinarily precise natural clocks, since an unmodeled mass in the solar system would slightly alter the arrival times of their pulses. Those constraints are weaker, but improving. So multiple independent lines of evidence are being brought to bear, none of which has found anything, and all of which are narrowing the space. The statistics change every time a distant object is discovered, and several have been found since 2016. Some have strengthened the clustering claim. Objects found on orbits consistent with the predicted alignment have been announced periodically, and the proponents have pointed to them as confirmations of the model's predictive power. Others have weakened it. Objects found on orbits that don't fit have also been announced, and the skeptics have pointed to those. There's a specific concern here, which is worth stating plainly. When a hypothesis predicts where objects should be, and telescope time is then allocated to search those regions, the resulting discoveries are not independent tests. You will find objects where you look. The proponents are aware of this and have been careful to distinguish objects found in targeted searches from those found serendipitously. The overall picture is that the sample of relevant objects has grown from around 6 to several dozen, and the statistical significance of the clustering has not increased dramatically as it grew, which skeptics regard as telling and proponents attribute to selection effects in the new discoveries. Which is, again, the same argument in a new form. The data are accumulating. The disagreement is about what they mean. There's an observatory in Chile that changes this question, and it's the reason most people in the field expect an answer within a decade. It sits on a mountain in the Atacama, and it carries the largest digital camera ever built for astronomy, over 3 billion pixels, producing images that would require hundreds of high-definition screens to display at full resolution. Its design is unusual, a wide field of view combined with a large mirror, which means it can photograph enormous areas of sky deeply and quickly. The plan is to survey the entire visible southern sky every few nights for 10 years, producing a continuous record of everything that changes or moves. For solar system objects, that's transformative. Instead of a handful of surveys covering scattered patches with different biases, there would be one uniform survey covering everything, with a fully characterized selection function. It's expected to increase the number of known trans-Neptunian objects by a large factor, from a few thousand to perhaps 40,000 or more. And that does two things at once. It could find the planet directly, if it's bright enough and in the surveyed region, and even if it doesn't, it would provide a sample of distant objects large enough and uniform enough that the clustering question could finally be answered statistically without arguments about bias. Let's be careful about expectations, because a direct detection isn't guaranteed. The survey's depth is expected to reach around magnitude 24 in a single visit, and deeper when many images are combined over years. If the planet is at the nearer end of the predicted range, say 400 astronomical units, it would likely be bright enough to detect. If it's at the far end, out past 700 or 800, it may be too faint even for this instrument, particularly if it's less reflective than assumed. There's also the sky coverage. The observatory sees the southern sky and part of the north, but not everything. And part of the predicted region lies in directions it observes poorly, or against the crowded background of the Milky Way, where a faint, slow-moving object is much harder to pick out. And there's the question of whether the object is currently in a favorable part of its orbit. So the realistic expectation is a good chance of a direct detection if the planet exists near the more favorable end of the parameter space, and, regardless, a decisive answer on whether the orbital clustering is real. That second outcome may be the more important one, because it determines whether there's anything to look for at all. Direct imaging isn't the only route, and several other methods have been proposed. One uses microwave telescopes. The experiments built to map the cosmic microwave background scan large areas of sky repeatedly at millimetre wavelengths, and a distant planet, warmed by whatever internal heat it retains, would emit faintly at those wavelengths. Because those instruments observe the same sky over and over, a moving source could in principle be extracted from the data by searching for objects that shift between observations. Searches have been carried out in existing data and have found nothing so far, but the sensitivity is improving. A second method is occultation. If the planet passes in front of a background star, the star would blink out briefly. Monitoring enough stars over enough time might catch such an event, though the probability for any particular star is minuscule, and you'd need to be watching the right patch. A third involves the long-period comets that fall in from the Oort cloud. Their orbits are shaped by whatever they pass on the way, and some researchers have looked for statistical signatures of a massive perturber in the distribution of their orbital elements. And a fourth, for the black hole variant, would be the brief flares produced as small bodies were disrupted and consumed. None has produced a detection, but the variety is worth noting. The question is being attacked from several directions at once. Suppose, one ordinary morning, an object turns up in the right place with the right motion. What happens next? First, confirmation. A single detection isn't enough. You need to observe it over months to establish that it's genuinely following a distant orbit, rather than being something closer and slower moving, or an artifact. Then the orbit is refined, which takes years. A fraction of an orbit that takes 15,000 years to complete gives only a short arc to work with. Then characterization. Its brightness and color would give a first estimate of size and surface composition. Spectroscopy, with a large enough telescope, might reveal what its atmosphere is made of. Then the naming, which is governed by the International Astronomical Union. Discoverers propose a name, and the relevant committee approves it. Planets are traditionally named for Roman deities, though the convention would be an interesting discussion, given that Pluto's reclassification is still a sore subject in some quarters. And then, presumably, decades of study. It would be the nearest example of the most common class of planet in the galaxy, a super-Earth or mini-Neptune, close enough to examine properly, which no telescope can do for the ones around other stars. That last point is the real prize, not the discovery itself, but having one of these things within reach. Let's do the practical question, because the numbers are sobering. At 500 astronomical units, the object would be about 75 billion kilometers away. For comparison, the Voyager spacecraft, launched in 1977, are currently around 160 to 200 astronomical units out after nearly 50 years of travel. At their speed, reaching 500 would take well over a century from launch. Faster options exist on paper. Concepts have been studied for missions using gravitational assists or solar sails, or a close pass by the Sun to gain speed. Some proposals suggest transit times of 20 to 50 years for missions to a few hundred astronomical units. None of that is currently funded or built, and all of it depends on technology that hasn't been demonstrated at the required scale. There's also the targeting problem. You'd need to know exactly where the object is and where it's going, which requires years of orbit determination after discovery. So a flyby is conceivable within a century of a discovery. And an orbiter is considerably harder, because slowing down at the far end requires enormous additional capability. Which means that if it's found, essentially everything we learn about it for a very long time would come from telescopes. Let's spend a chapter imagining the place, because it's a peaceful thing to picture. The Sun would be a point of light. Bright, considerably brighter than any star in our sky, perhaps comparable to a very bright planet, but a point, with no disk, casting a faint sharp shadow if there were anything to cast it on. The daylight, such as it is, would be roughly the brightness of a well-lit room at night, enough to see by if your eyes were adapted, not enough to warm anything. The temperature would be a few tens of degrees above absolute zero, cold enough that nitrogen would be frozen solid, and any atmosphere would be hydrogen and helium retained from formation, rather than anything that could condense. A year would last 10 to 20,000 years. If it has seasons at all, from an axial tilt, each would last thousands of years. The sky would be spectacular in one respect. With essentially no scattered light, the stars would be extraordinarily sharp and numerous, and the band of the Milky Way would be brilliant. And our own Sun would be one of those points, indistinguishable to the eye from the others except by being brighter, and by the fact that everything there is bound to it. Let's take the other outcome seriously, because it's at least as likely. Suppose the survey completes, the statistics become unambiguous, and the clustering turns out to be a selection effect. What then? Several things. The unexplained objects remain unexplained. Sedna's detached orbit still needs a cause, and the leading alternative is a close stellar encounter early in the Sun's history, when it was still in its birth cluster. That's a perfectly good explanation, and it may well be the right one. It predicts that the detached objects are fossils of an event 4.5 billion years ago, rather than evidence of something present now. The perpendicular orbits and the Sun's tilt would need other explanations, and candidates exist for both. And the search would have produced an enormous amount of incidental science, a catalogue of tens of thousands of distant objects, mapping the structure of the outer solar system in detail for the first time. That's the thing about a well-posed question. Answering it in the negative still requires building the instrument and doing the survey, and the survey is valuable regardless. Michael Brown has said publicly that he'd find a null result disappointing but scientifically fine, which is roughly the right attitude, and not always the one people manage. Let's go back and tell the story of how the outer solar system was opened up, because it took decades of patience. The idea that there might be a population of small bodies beyond Neptune goes back to the 1940s and 50s, proposed independently by several astronomers, including Gerard Kuiper, though his version had the belt cleared out rather than populated. The reasoning was simple. The disk of material that formed the planets shouldn't have stopped abruptly at Neptune. There should be leftovers further out, too sparse to have formed anything large. For decades, nobody found any. The objects are small, dark, and enormously distant, and photographic plates weren't sensitive enough. Then, in 1987, two astronomers, David Dewitt and Jane Liu, began a systematic search using the newly available electronic detectors, which are far more sensitive than photographic film. They looked for 5 years, examining field after field, finding nothing. Dewitt later described it as a period of considerable doubt about whether they were wasting their careers. In August 1992, they found one, a faint reddish object beyond Neptune's orbit, perhaps 200 kilometers across. And once the technique was proven, the discoveries accelerated. Within a decade, there were hundreds. Today, there are thousands, and the outer solar system went from an empty theoretical region to a mapped and populated one within a single career. That flood of discoveries created a problem, and its resolution is why the phrase Planet 9 carries some baggage. As larger objects were found beyond Neptune, the question of what counts as a planet became pressing. If Pluto is a planet, what about an object almost as large? What about one larger? In 2005, Michael Brown's team, the same Brown of tonight's story, announced the discovery of an object initially thought to be larger than Pluto, later determined to be slightly smaller but more massive. It was eventually named Eris, after the goddess of discord, which was an appropriate choice, because it forced the issue. Either Eris was the 10th planet, or Pluto wasn't the 9th. In 2006, the International Astronomical Union voted on a definition, requiring a planet to orbit the Sun, be round under its own gravity, and have cleared its orbital neighborhood of other bodies. Pluto fails the third condition. It shares its region with many other objects, and was reclassified as a dwarf planet. The decision remains contentious. Some planetary scientists object to the clearing criterion as poorly defined and unhelpful, and Brown, who has occasionally referred to himself as the man who killed Pluto, is now the leading proponent of a 9th planet, which is a pleasing irony that he has acknowledged. Since Sedna, more detached objects have been found, and they're collectively called sednoids. The definition varies, but roughly, objects whose closest approach to the Sun stays beyond about 50 or 60 astronomical units, well outside Neptune's influence, on orbits extending far beyond. Only a handful are known. Sedna, the object nicknamed Biden, and a small number of others found since. Each discovery is significant precisely because there are so few. They're difficult to find because they spend the overwhelming majority of their long orbits far from the Sun and therefore extremely faint. We can only detect them near their closest approach, which means the known ones are a small and biased sample of a possibly much larger population. Estimates of that population vary widely. Some suggest there could be hundreds or thousands of Sedna-sized objects out there, with only the nearest few detectable. And every one of them needs an explanation, because none can be produced by the known planets. So there's a genuine puzzle here that exists independently of the clustering argument. A population of objects on orbits that the current solar system cannot generate, requiring something else to have shaped them. The main alternative explanation for those detached orbits is worth a chapter, because it's plausible and it doesn't require anything to be there now. Stars don't form alone. They form in clusters, hundreds or thousands together, from a single collapsing cloud, and remain in close proximity for tens or hundreds of millions of years before the cluster disperses. During that period, the Sun would have had neighbors far closer than any star is today. Encounters within a few thousand astronomical units would have been common. And a passing star's gravity can lift the closest approach of a scattered object, taking something that Neptune had flung outward and detaching it, leaving it on an orbit that no longer comes back to Neptune's reach. That's exactly what Sedna needs. And the timing works. It would have happened in the first 100 million years, when the Sun was still in its birth cluster. Simulations of this process produce populations of detached objects with a range of orbits, and some of them look reasonably like what we observe. The difficulty is in the details, matching the specific distribution of the known objects, and explaining why they'd cluster in orientation if they do. But it's a serious alternative. It requires no undiscovered planet, and it may well be the answer. That raises something worth a chapter of its own, because it's easy to forget. The Sun was born in a cluster, along with perhaps 1,000 or several thousand other stars, from a single cloud of gas and dust about 4.5 billion years ago. Those stars are still out there. They've been scattered around the galaxy over billions of years by the ordinary shear of galactic rotation, and they're now spread across a substantial fraction of the disk. Astronomers have searched for them, looking for stars with the same age and the same chemical composition, which would suggest a common origin. A few candidates have been proposed, none confirmed beyond doubt. Meanwhile, the traces of that early crowded period may be written into the outer solar system. The detached objects. The outer edge of the Kuiper belt, which appears to end rather abruptly around 50 astronomical units for reasons that aren't fully understood. Possibly the presence or absence of a distant planet. So the question we're asking tonight may ultimately be a question about the Sun's childhood, about what happened during the first 100 million years in a crowded neighborhood that dispersed long ago. And the evidence for that period is preserved almost nowhere else. The inner solar system has been reprocessed thoroughly. The outer regions are cold and slow and largely undisturbed. Let's go further out, because there's a whole region beyond everything we've discussed. Long-period comets arrive from all directions on enormously elongated orbits, with periods of thousands or millions of years. They don't come from the plane of the solar system, they come from everywhere. In 1950, the Dutch astronomer Jan Oort analyzed their orbits and concluded that they must originate in a vast spherical shell surrounding the solar system, extending from a few thousand out to perhaps 100,000 astronomical units. That's the Oort cloud. It's never been directly observed. Its members are small, dark, and so distant that no telescope could detect an individual one. But its existence is well supported by the comet orbits, and estimates suggest it contains trillions of icy bodies, totaling perhaps a few Earth masses. Its objects are thought to have formed much closer in, among the giant planets, and been scattered outward early on, then had their orbits lifted and randomized by passing stars and by the gravitational tide of the galaxy itself. Occasionally, something disturbs one, and it falls inward, and we see a comet. So the Sun's realm has a structure we've only partly mapped. Planets, then a belt, then a scattered disk, then the detached objects, and then a vast unseen shell of ice, reaching a substantial fraction of the way to the nearest star. Something worth a chapter, because it changed how people think about what's out there. In October 2017, a survey in Hawaii found an object moving too fast to be bound to the Sun. Its trajectory was hyperbolic. It had come in from interstellar space, swung around the Sun, and was leaving. It was named Oumuamua, a Hawaiian word meaning something like a scout or messenger from the distant past. It was small, perhaps a few hundred meters, and extremely elongated. Its brightness varied dramatically as it tumbled, suggesting a shape unlike anything in our solar system. It showed no cometary tail, and it accelerated slightly in a way that wasn't fully explained by gravity. Various explanations were proposed, including outgassing of unusual ices. It passed out of range before anyone could study it properly. Then, in 2019, a second interstellar object was found. This one plainly a comet, with a tail, behaving in an entirely ordinary way apart from its trajectory. And a third was reported more recently. What they tell us is that interstellar objects pass through regularly. The estimated population implies that a great many wander the galaxy, material ejected from other planetary systems, drifting between the stars. Which makes the catcher hypothesis for a distant planet slightly less far-fetched. If small objects pass through constantly, larger ones must too, and occasionally one might be caught. That leads to a related population, and it's larger than most people expect. Free-floating planets, sometimes called rogue planets, are objects of planetary mass that aren't orbiting any star. They drift through the galaxy alone, in permanent darkness. They're detected by microlensing. When such an object passes almost exactly in front of a distant star, its gravity briefly focuses the star's light, producing a characteristic brightening lasting hours or days. Surveys monitoring millions of stars have found a number of such events, with durations implying planetary masses and no accompanying star. Estimates of the population vary considerably, but some analyses suggest free-floating planets may be comparable in number to stars, or more numerous still, meaning billions or trillions in our galaxy. Most are thought to have formed in planetary systems and been ejected during the chaotic early period, when gravitational encounters between forming planets were common. Some may have formed alone, in small collapsing clouds too sparse to make a star. Either way, the galaxy contains an enormous number of dark planetary mass objects between the stars, and the possibility that our Sun captured one early on is not the outlandish suggestion it once seemed. Let's spend a chapter on the material out there, because it's a peaceful thing to picture. Trans-Neptunian objects are mixtures of ice and rock, with surfaces darkened and reddened by billions of years of exposure to cosmic radiation. The ices include water, but also methane, nitrogen, carbon monoxide and ammonia, substances that are gases here and solids at those temperatures. Their colors vary considerably. Some are strikingly red, which is thought to come from complex organic compounds produced when radiation processes simple ices, a class of material sometimes called tholins. Others are neutral gray. The color distribution appears to correlate with orbital properties, which suggests different populations formed at different distances and have different histories. Sizes range from the few known large ones, Pluto and Eris, around 2,000 kilometers, down through hundreds of objects, a few hundred kilometers across, and presumably enormous numbers of smaller ones below detection. Many have moons. Pluto has 5. A substantial fraction of the larger objects have at least one companion, which is useful because a moon's orbit reveals the primary's mass. And they're old. Unlike anything in the inner solar system, these bodies have never been heated significantly, never been reprocessed, never been geologically active in any substantial way. They're leftovers, essentially unchanged, since the solar system formed. There's one object out there we've seen up close, and it's worth a chapter because of what it showed. After flying past Pluto in 2015, The New Horizons spacecraft was targeted at a small Kuiper Belt object and reached it on the 1st of January 2019. The object was named Arrokoth, a Powhatan word meaning sky, and it's about 36 kilometers long. And it turned out to be two lobes joined at a narrow neck, like a flattened snowman. Two objects that had come together gently at walking pace and stuck. That's important, because it tells us how objects out there formed, not by violent collisions and accretion, but by gentle assembly, clumps of small particles collapsing together and merging softly. It's also extraordinarily flat. Both lobes are much more pancake-shaped than expected, which no one had predicted and which is still being explained. And it's pristine. It has been at that distance, at that temperature, for 4.5 billion years, essentially untouched. Its surface is the original material of the solar nebula, chemically processed by radiation but never melted, never differentiated, never disturbed. So there's an object at the edge of the mapped solar system, photographed at close range, which is essentially a preserved sample of how planet formation began. Since we keep saying the edge, let's spend a chapter clarifying what that means, because there are several different edges. The first is the heliopause, the boundary where the solar wind, the stream of charged particles blowing off the sun, is finally stopped by the pressure of the interstellar medium. That sits at around 120 astronomical units, and both Voyager spacecraft have crossed it, the first in 2012, the second in 2018. They detected a clear change, a drop in solar particles, a rise in cosmic rays from outside, and a shift in the magnetic field. That's often reported as leaving the solar system, and in one sense it is. They're outside the sun's magnetic bubble. But gravitationally, they're nowhere near leaving. The sun's gravitational domain extends thousands of times further, and the Voyagers are still bound to it. They'll continue orbiting the galaxy alongside the sun for a very long time. The second edge is the outer boundary of the Kuiper Belt, which appears to end rather abruptly around 50 astronomical units, a fact that remains unexplained and which some have suggested might itself indicate a large perturber. And the third is the gravitational boundary, out near 2 light-years, where the sun's pull gives way to the galaxies. So the edge means 3 different things at 3 wildly different distances. Tonight's hypothetical planet would sit between the first and the third, well outside the solar wind's bubble, well inside the gravitational domain. Let's spend a chapter on the technique, because it's changed remarkably little in principle since 1930. Clyde Tomball's method was to photograph the same patch of sky on 2 nights, then compare the plates using a device called a blink comparator, which alternates rapidly between 2 images so that anything that has moved appears to jump back and forth while the fixed stars stay still. He examined millions of star images that way, by eye for months. Finding Pluto meant noticing a single point that shifted slightly between 2 plates crowded with tens of thousands of stars. The modern approach is the same idea, automated. Digital images of the same field are taken at intervals, aligned precisely, and subtracted from one another. Everything that stayed put cancels out. Anything that moved or changed remains. Software then flags the candidates, and most turn out to be artifacts. Cosmic ray hits on the detector, imperfect subtraction near bright stars, satellites crossing the field. For very distant objects, there's an additional difficulty. They move so slowly that a single night's images may show no detectable motion at all. So the technique is to combine many images taken along a hypothesized path, shifting each one by the amount the object would have moved, and add them up. That's called shift and stack, and it can pull out objects far too faint to see in any individual image. It requires trying enormous numbers of possible trajectories, which is computationally demanding but entirely feasible now. There's a role for people in this, which is unusual in modern astronomy, and it deserves a chapter. Several projects invite volunteers to examine images for moving objects, presenting short animations of the same patch of sky at different times, and asking users to flag anything that shifts. The reason isn't nostalgia. Human visual systems remain better than software at certain tasks, particularly rejecting the odd artifacts that arise near bright stars, in image edges, and in regions of complex background. One such project uses infrared survey data, and volunteers have found a substantial number of brown dwarfs and faint nearby objects, including some of the coolest known. Several discoveries have been credited to volunteers by name in professional papers. None has found the planet, but the searches continue, and each one that comes up empty narrows the possibilities. There's something appealing about that continuity. Tombaugh found Pluto by staring at plates for months. A century later, people are staring at animations on their laptops, doing essentially the same task with better images, and occasionally finding something. Let's spend a chapter on the sociology, because the way this dispute is being conducted is worth noticing. The two sides have published against each other for a decade. The exchanges have been direct, sometimes pointed, and occasionally public in a way that scientific disagreements often aren't. But they've also been productive. Each critique has prompted better analysis. The proponents have developed increasingly sophisticated models of survey selection effects. The skeptics have been forced to state precisely what would constitute evidence. And both sides agree on what would settle it. Better data from a uniform survey or a direct detection. That's the crucial feature. This is a falsifiable claim with a defined path to resolution, and everyone involved has said publicly what would change their mind. Michael Brown has stated that if the large survey completes without finding the planet and the clustering evaporates, he'll accept it. The skeptics have stated that a detection would settle it in the other direction. Which is how these things are supposed to work, and it doesn't always happen. Plenty of disputes drag on because the sides disagree about what the evidence would even look like. Here the disagreement is about what current data show, not about what would count. That's a healthy position, and it's why the question will close within a decade rather than lingering indefinitely. A light chapter on naming, because it's a real question and the conventions are specific. The International Astronomical Union governs the naming of solar system objects through committees for different categories. The convention for planets has been Roman deities, which is why we have Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, which is Greek and stands out slightly, and Neptune, which returned to convention. For trans-Neptunian objects, the convention has been mythological figures associated with creation or the underworld, drawn from a range of cultures, hence Sedna from Inuit tradition, Quawa from the Tongva people of Southern California, Makemake from Rapa Nui, Haumea from Hawaiian tradition. If a genuine planet were found, there would presumably be a discussion about which convention applies, and given how contentious Pluto's reclassification remains, that discussion might be lively. The proposers have generally avoided suggesting names, which is sensible. Naming something before you found it invites embarrassment. For now, the working term is Planet 9, which some object to on the grounds that it implicitly endorses Pluto's demotion. An alternative sometimes used is Planet X, which has its own baggage from Lowell, and which skeptics occasionally use in a pointed way. Whatever it ends up being called, if it's called anything, the name will outlast everyone involved in the argument. Let's follow one object forward, because it puts the timescales in perspective. Sedna is currently approaching its closest point to the Sun, which it will reach around the middle of this century, the first time in 11,000 years. At that closest approach, it will be about 76 astronomical units out, still more than twice Neptune's distance, still extremely cold, still faint. But it's the brightest it will be for another 11,000 years, which makes the next few decades the only realistic window for studying it in detail with current or near-future instruments. There have been proposals for a mission, a flyby, launched in the next couple of decades, arriving in the 2030s or 40s, while Sedna is comparatively close. After that, it recedes. Over the following 5,500 years, it will travel out to around 900 astronomical units, becoming steadily fainter, and then begin the long fall back. The last time it was here, human beings were beginning to farm. The next time, whatever exists then, will have no records from now. There's something quietly moving about that. A 1,000-kilometer ball of ice on an 11,000-year circuit, arriving at the nearest point in its orbit during the few decades when a species on the third planet happens to have telescopes capable of seeing it. Let's lay out the quantities in one place, slowly, because it's satisfying to have them in order. Neptune, 30 astronomical units. The Kuiper Belt, 30 to 50. The scattered disk, out to a few hundred. The detached objects, closest approaches of 76 and 80 and beyond. The proposed planet, mass around 5 to 7 Earth masses in recent estimates. Average distance, somewhere between 400–600 astronomical units, orbital period, 10 to 20,000 years. Predicted brightness around magnitude 22 to 25. The Oort cloud, a few thousand to perhaps 100,000 astronomical units. The Sun's gravitational domain, something like 1.5 to 2 light years, which is 100,000 to 150,000 astronomical units. Known trans-Neptunian objects, a few thousand. Expected after the new survey, perhaps 40,000. Objects in the clustering sample, originally 6, now several dozen depending on the selection criteria, which is precisely the difficulty. Time until the question is likely settled, roughly a decade, perhaps 2. And the fraction of the Sun's realm that has been surveyed to the depth needed to find such an object, small. Not negligible. A substantial part of the plausible region has been covered, but far from complete. Let's spend a chapter distinguishing this proposal from the long history of failed distant planets, because the distinction matters. Nemesis and Tyche were proposed to explain patterns in extinction records and comet orbits, datasets whose reliability was itself contested, and both proposed objects massive enough to have been detected by existing surveys. Both were cleanly excluded. Lowell's Planet X was proposed to explain residuals in Uranus and Neptune's orbits that turned out not to exist. Vulcan was proposed to explain a real anomaly that had a different cause entirely. This proposal differs in several ways. The proposed object is small enough to have escaped all existing surveys, so its non-detection so far is not evidence against it. The mass and orbit are in a range that's physically reasonable and matches the most common planet type known, and the model made specific predictions about objects that hadn't been discovered when it was published, some of which have since been found. It also differs in being taken seriously by its own critics. The skeptics don't argue that the idea is absurd. They argue that the data supporting it are not yet strong enough, which is a much narrower claim. That's a substantially better position than any previous proposal occupied, which is why it has survived a decade of scrutiny without either being confirmed or dismissed. Let's be honest about the gaps, because they're substantial and central. We don't know whether the orbital clustering is real. That's the fundamental question, and competent people reach opposite conclusions from the same data. We don't know whether the detached objects require a present-day perturber or a past stellar encounter. We don't know the total mass of small bodies in the outer solar system, which determines whether the disk alternative is viable. We don't know why the Kuiper Belt appears to end abruptly at 50 astronomical units. We don't know how the Sun's 6-degree tilt arose, and whether a distant planet is the explanation or one of several possibilities. And we don't know how many large objects remain undiscovered beyond Neptune generally. The surveys are incomplete, and the population estimates have wide uncertainties. What we do know is that there is a great deal of room out there, that it has been only partially searched, and that at least a handful of objects are on orbits the known solar system cannot produce. That last point stands regardless of how the planet question resolves. Something shaped those orbits. The argument is about whether it's still there. Let's take stock, gently, before we start winding down. The observation at the heart of this is that a small number of very distant objects appear to have orbits oriented in a similar direction, which shouldn't happen by chance and shouldn't survive 4.5 billion years without something maintaining it. The proposed explanation is a planet of several Earth masses, on a long, elongated orbit, averaging several hundred astronomical units, shepherding those orbits through resonant gravitational interaction. The same hypothesis appears to account for several other features: the detached objects, the perpendicular orbits, the Sun's tilt, which it wasn't designed to address. The principal objection is that the sample is small, and the surveys that found it had biases that are difficult to characterize after the fact, and that the apparent clustering may be an artifact of where people happen to look. Neither side has been able to convince the other, and the disagreement is genuinely about the data rather than about the plausibility of the idea. So the honest answer to tonight's question is, possibly. There is a real pattern in the data that might be real, or might be a selection effect. There is a reasonable physical explanation if it's real. Extensive searching has found nothing, and a survey now beginning should settle it within a decade or so. Which is a comfortable place to leave it. The question is well posed. The answer is coming, and nothing about it requires anything from anyone tonight. Let's spend a chapter on the mechanism, because a planet organizes their orbits needs unpacking. The relevant idea is resonance. When two objects orbit, the Sun with periods in a simple ratio, one going round twice for every 3 circuits of the other, say, their gravitational tugs repeat in the same pattern each cycle rather than averaging out. Repeated tugs at the same points can either destabilize an orbit or protect it, depending on the geometry. The proposed planet is thought to act mainly through a slower kind of interaction, in which the shapes and orientations of orbits are exchanged over very long times, rather than positions being locked directly. The specific claim is that objects whose long axes point in the opposite direction to the planets are dynamically stable, because the arrangement keeps them from ever having a close encounter with it. Objects pointing the same way are unstable and get removed over billions of years. So the planet doesn't gather them into alignment so much as clear out everything that isn't aligned. What survives is what was protected. That's a common pattern in solar system dynamics. The gaps in Saturn's rings and in the asteroid belt work the same way. Resonances with a massive body remove material at particular distances, leaving structure behind. So the claim isn't that a planet is herding objects into place. It's that a planet has been quietly removing the ones pointing the wrong way for 4.5 billion years. There's a related mechanism that explains one of the stranger predictions, and it's worth a chapter. Some objects have been found on orbits tilted almost perpendicular to the plane of the solar system, going around the Sun nearly at right angles to everything else. That's a peculiar place to be, and there's no obvious way to get there from the flat disk the planet's formed in. But there's a known dynamical process, worked out in the 1960s, in which a distant perturber can drive an orbit through cycles. As the tilt increases, the elongation decreases, and vice versa, exchanging one for the other over long periods. Under the right conditions, that process can drive an orbit from the plane all the way up to nearly perpendicular, and then back down again over tens of millions of years. The simulations of the proposed planet produce exactly that: a population of objects driven onto high-inclination orbits, some nearly polar. And a handful of such objects were known when the paper was published, with more found since. The skeptics point out that other mechanisms can also produce high-inclination objects, and that the sample is small. But it's one of the model's genuine predictions, and it wasn't put in by hand. Let's spend a chapter on how these claims are tested, because the computation is more demanding than it sounds. To determine whether a hypothetical planet produces the observed pattern, you simulate the outer solar system, the known planets, the hypothetical one, and a large population of test objects, integrated forward for billions of years. The difficulty is that these systems are chaotic. Tiny differences in initial conditions grow exponentially, so individual trajectories become unpredictable after a certain time. Which means you can't simulate one object and draw conclusions. You simulate thousands, with slightly varied starting conditions, and look at the statistical properties of the population. How many end up aligned? How many are ejected? How the distribution evolves? And you have to do that for many different assumed planets, different masses, distances, eccentricities, orientations, to map which ones produce the observed pattern. That's a large computation, and the results depend on choices: how long you run it, how you set up the initial population, what you count as a match. Different groups make different choices and get somewhat different answers, which is one reason the dispute persists. There's also a numerical concern. Integrating orbits for billions of years accumulates errors, and specialized methods are needed to keep them under control over that many steps. There's a piece of context that makes a distant planet more plausible, and it's now the standard picture of how our system formed. The planets are not where they formed. In the current models, the giant planets began on more closely spaced orbits and migrated substantially, driven by interactions with the disk of remaining material and with each other. In one widely discussed scenario, Jupiter and Saturn passed through a resonance, which destabilized the whole outer system. Uranus and Neptune were flung outward, possibly swapping places, and Neptune plowed outward through the disk of small bodies. That migration scattered an enormous number of objects, some inward, producing a period of heavy bombardment in the inner solar system, and some outward, populating the scattered disk and the Oort cloud. There's good evidence for it in the Kuiper belt. A substantial population sits in resonances with Neptune, which is what you'd expect if Neptune swept outward and captured objects into those resonances as it went. And in some versions of the model, there was originally a fifth giant planet, which was ejected during the instability, which would make the solar system a system that has already lost a planet. Against that background, the idea of an additional object flung to a distant orbit is not exotic. It's the sort of thing the standard formation picture produces routinely. There's a group of objects worth a chapter, because they're the quietest things in the solar system. Most Kuiper belt objects have been scattered, resonantly captured, or otherwise disturbed by Neptune's migration. Their orbits are tilted and elongated, bearing the marks of that violent early period. But there's a subset, called the cold classical population, that appears to have avoided all of it. They orbit between about 42 and 47 astronomical units on nearly circular paths with very low tilts. They're also distinctive in other ways. They're redder than other populations. They include an unusually high fraction of binaries, pairs orbiting each other, and those binaries are loosely bound, which means they'd have been broken apart by any close encounter. The interpretation is that these objects formed where they are and have never been disturbed. They're the only population in the solar system that can plausibly claim that. Arrokoth, the flattened snowman visited by New Horizons, belongs to this group, which is why its gentle two-lobed structure is so informative. So there's a narrow ring out beyond Neptune, containing objects that have been sitting undisturbed on quiet circular orbits since the solar system formed, while everything around them was scattered, tilted, and rearranged. A short technical chapter, because the brightness numbers keep coming up. Astronomers measure brightness in magnitudes, a scale inherited from the ancient Greeks, who ranked the visible stars from first magnitude for the brightest to sixth for the faintest. It was later formalized, with the peculiar consequence that the scale runs backwards. Larger numbers mean fainter objects, and is logarithmic, with 5 magnitudes corresponding to a factor of 100 in brightness. On that scale, the brightest stars are around 0. The faintest visible to the unaided eye from a dark site are around 6. Binoculars reach about 10. A good amateur telescope perhaps 14 or 15. Pluto is around magnitude 14. Most known Kuiper belt objects are 20 to 23. The proposed planet is estimated at somewhere between 22 and 25, depending on its distance and how reflective it is. For context, 25 is about 40 million times fainter than the faintest star you can see. Reaching it requires a large telescope and a long exposure, which is exactly what the new survey provides, and why it changes the situation. Let's spend a chapter on the practical obstacles, because they shape where searchers have looked. The sky is never entirely dark. Even at the best sites on a moonless night, there's airglow, faint emission from the upper atmosphere, plus scattered starlight and zodiacal light from dust in the solar system. That background sets a flaw. To detect a faint object, you need its light to exceed the noise from that background, which means longer exposures and larger telescopes. The moon makes it dramatically worse. Near full moon, the sky is many times brighter, and deep searches become impossible. So surveys work around the lunar cycle, using bright nights for other programs. Then there's the Milky Way. Part of the predicted region for the hypothetical planet lies toward the galactic plane, where the density of stars is enormous. Picking out a faint slow-moving point against a field crowded with tens of thousands of stars is far harder than against empty sky. That's a genuine gap in the search coverage, and it's been acknowledged by both sides. And finally, there's timing. Any given patch of sky is only observable for part of the year, when it's up at night rather than behind the sun. A full search requires observing over multiple years to cover everything. Let's spend a chapter on the instrument itself, because it's a remarkable object. The camera at the new observatory in Chile weighs about 3 tons and is roughly the size of a small car. Its focal plane holds 189 individual detectors, tiled into a single surface about 60 centimeters across. Together, they provide over 3 billion pixels. A single image covers a patch of sky about 40 times the area of the full moon, enormous for a telescope of that size, and requiring an unusual optical design. Each exposure lasts about 30 seconds, and the telescope then moves to the next field within a few seconds. That slewing speed required the whole structure to be built unusually compact and stiff. Over a night, it takes something like 1,000 exposures. The data volume is around 20 terabytes per night, processed automatically, with alerts issued for anything that changed within about a minute of the image being taken. Over 10 years, it will image the same fields hundreds of times over, which is what makes deep combination possible, and what allows very faint, slow-moving objects to be extracted by stacking many exposures along a hypothesized path. That's the machine that should answer tonight's question. The survey isn't designed for this question, and the incidental yield is enormous. It will find millions of supernovae over 10 years, compared to the thousands known now, transforming the study of stellar death and of the expansion history. It will map the shapes of billions of galaxies, measuring the subtle distortions caused by gravitational lensing, which constrains dark matter and dark energy. It will catalogue the Milky Way in unprecedented detail, finding faint stellar streams and dwarf galaxies. It will discover an estimated 5 million asteroids. And it will find things nobody has thought of, because a survey that photographs the whole sky repeatedly for a decade inevitably catches phenomena that targeted observations miss. That happened with the previous generation. A giant comet found in archival data, interstellar visitors, entire classes of transient events that hadn't been predicted. So the search for a distant planet is one line item in a program, whose main purpose is everything else, which is how large surveys are usually justified, and why they tend to be so productive. Let's return to one of the supporting arguments, because it's the one I find most intriguing. The planets all orbit in roughly the same plane, a legacy of forming from a flattened rotating disk. The Sun rotates too, and its equator should lie in that same plane for the same reason. Everything formed from the same spinning cloud. But it doesn't quite. The Sun's rotation axis is tilted about 6 degrees relative to the plane of the planets, an angle too large to be an accident of formation and too small to suggest anything dramatic. It has never had a compelling explanation. The proposed planet offers one. A massive body on a tilted distant orbit would exert a slow torque on the plane of the inner planets over billions of years, gradually tipping it relative to the Sun's spin, and the calculations produce roughly the observed amount. That's an appealing bonus. Since the tilt was a pre-existing puzzle, the model wasn't built to solve. Other explanations exist: a passing star early on, or an asymmetry in the original cloud's collapse. So it's suggestive rather than decisive. But it's one more thing that would be neatly accounted for. Here's a thought worth a chapter, and it's a quiet one. If the planet exists, it's on an orbit taking 10 to 20,000 years, and it spends most of that time far from the Sun, moving slowly at its faintest. Which means whether it's currently findable depends partly on where it happens to be right now. Near its closest approach, it would be considerably brighter and easier to detect. Near its furthest point, well beyond 1,000 astronomical units, it might be beyond the reach of even the new survey. And the dynamics actually favor the far end, because an object spends most of its time there, which is one reason the searches have come up empty. So there's a real possibility that the answer is, it's there, and it's currently too distant to see, and it will be for the next several thousand years. That would be an unsatisfying outcome. A planet inferred, but not confirmable within any human timescale. It isn't the most likely case. The survey should reach most of the plausible range. But it's a reminder that the resolvability of this question depends on an orbital phase nobody chose. Let's spend a reflective chapter on why this question gets so much attention, because the disproportion is worth noticing. Scientifically, it's a moderately important question about solar system dynamics. It would be a nice discovery. It would give us a nearby example of a common planet type, and it would tell us something about the Sun's early history. Publicly, it's enormous, generating headlines regularly, appearing in documentaries, with a level of recognition few open questions in astronomy achieve. Part of that is the framing, something hidden, close by, undiscovered. That's a very old narrative shape, and it lands regardless of the details. Part is accessibility. Most open questions in astrophysics require substantial background to appreciate. This one is graspable in a sentence. And part, I suspect, is that it restores something. The solar system had been thoroughly mapped. The era of discovering planets in it was over. The suggestion that it isn't over is appealing. I don't think there's anything wrong with that. The attention has funded searches and prompted careful work on both sides. But it's worth holding the proportion. The evidence is contested, the object may not exist, and the world would be much the same either way. Let's take a chapter to simply sit in the region we've been discussing, because it's a restful place to picture. At 500 astronomical units, the Sun is a bright point and nothing more. There is no daylight in any meaningful sense. The temperature is a few tens of degrees above absolute zero. Every substance you're familiar with, water, nitrogen, carbon dioxide, methane, is frozen solid. Nothing moves quickly. Orbital speeds are around 1 kilometer per second against the Earth's 30. An object there takes millennia to complete a circuit and drifts across the sky by imperceptible amounts over a human lifetime. There is almost no material. The density of anything at all is lower than the best vacuum achievable in a laboratory. And it's quiet in the fullest sense. No sound could propagate, no weather, no processes on any timescale a person would notice. A body out there could sit unchanged for 1 billion years. That's the setting. An enormous dark volume, extraordinarily cold, almost entirely empty, with the Sun as a distant bright star. And somewhere in it possibly, a world several times the size of ours, going round once every 15,000 years, and having done so since before there was an Earth. Let's end the substance with what a discovery would actually mean, because it's less than the headlines and also more. Practically nothing. It's unreachable. It has no effect on anything here, and its existence changes no aspect of daily life. Scientifically, several things. It would be the closest example of a super-Earth or mini-Neptune, the most common type of planet in the galaxy, and one we have no local specimen of. It would tell us something about the Sun's formation and early history, whether the system scattered a planet outward or captured one, or something else entirely. It would explain the detached objects, the perpendicular orbits, and possibly the Sun's tilt, closing several open questions at once. And it would demonstrate that the method still works, that you can infer an unseen mass from the motion of things you can see and then go and find it, as Lee Verrier did in 1846. It would also be the first new planet in our solar system since that year, which is a long enough gap that nobody alive has experienced one. There's a technique worth a chapter, because it's how many discoveries are actually confirmed. When a new object is found, its orbit is initially poorly known. A few observations over a few nights give only a short arc, and many possible orbits fit. The solution is recovery, searching archival images for the same object at earlier dates. If you can find it in photographs taken years or decades ago, the arc lengthens enormously and the orbit tightens. That requires knowing where to look, which requires a preliminary orbit, which requires the recent observations, so it's iterative. And it requires archives. Astronomical images from the past century have been increasingly digitized and made searchable, and some discoveries have been traced back to photographic plates from decades before the object was recognized. Pluto famously appears on plates taken years before Tombaugh found it, including some from Lowell's own earlier searches, where it was present and missed. For a distant planet, recovery would be crucial. A confident orbit would need observations spanning years, and finding it in existing survey data would accelerate that enormously. Which is why several searches have focused on re-examining archives rather than taking new images. The object may already have been photographed repeatedly and simply not noticed. Let's spend a chapter on that problem, because it's less straightforward than it sounds. An orbit is described by 6 numbers: size, shape, tilt, and 3 angles specifying orientation and timing. Determining them requires observations separated widely enough that the object's motion reveals the geometry. For an object with a 15,000-year period, a few years of observation covers a tiny fraction of one orbit, a very short arc. From a short arc, many quite different orbits can fit the data equally well. The distance in particular is poorly constrained, because an object moving slowly could be nearby and genuinely slow, or far away and moving fast. Astronomers use additional information to break the degeneracy, how the object's apparent position shifts over the year as the Earth moves, which gives a parallax and therefore a distance. Even so, orbits of distant objects typically carry substantial uncertainties for years after discovery, and the published values shift as more data accumulate. Which matters for tonight's question, because the clustering analysis depends on those orbital elements, and some of the objects in the sample have arcs shorter than one might like. That's another strand of the dispute, whether the orbits are known well enough for the statistical claim to be sound. Chad Trujillo and Scott Shepard, who raised the clustering question in 2014, have continued searching, and their program deserves a chapter. They've been running a systematic survey of the outer solar system for well over a decade, using large telescopes in Chile and Hawaii, deliberately covering regions where distant objects might be found. It has produced a substantial fraction of the known extreme trans-Neptunian objects, including several of the ones central to the clustering debate. They've also found objects at record distances, including bodies detected beyond 100 astronomical units, which are among the most distant solar system objects ever observed at the time of discovery. Shepard has additionally found large numbers of moons around the giant planets, using the same wide-field deep imaging techniques. Their position on Planet 9 has been notably measured. Having raised the possibility, they've generally described the evidence as suggestive rather than conclusive, and have emphasized that their surveys are designed to find objects regardless of whether they fit the hypothesis. Which is the right posture for people whose data underpins a contested claim. And it's worth noting, since we've discussed distant worlds abstractly, let's spend a chapter on the one we've seen properly. Before 2015, Pluto was a handful of pixels. Expectations were modest: a cold, cratered, geologically dead ball of ice, essentially unchanged for billions of years. The flyby overturned that within hours of the first images arriving. There are mountains of water ice several kilometers high. There's a vast plain of nitrogen ice, roughly 1,000 kilometers across, with almost no craters, meaning its surface is geologically young, being renewed continuously. That plain is divided into polygonal cells tens of kilometers wide, which are understood as convection cells. The nitrogen ice is slowly overturning, driven by heat from below, on timescales of perhaps 1,000,000 years per cycle. There are what appear to be cryovolcanic features. There's a thin nitrogen atmosphere with layers of haze. There are dunes, apparently of methane ice grains. And the object is tiny and extraordinarily cold, at 40 astronomical units, where the sun provides almost nothing. Which teaches something directly relevant to tonight. Distant worlds are not necessarily inert. Internal heat, retained from formation and from radioactive decay, can drive activity for billions of years, whatever the sunlight. That deserves a chapter, because it's why a distant planet wouldn't simply be a frozen rock. Every rocky body contains radioactive isotopes, uranium, thorium, potassium, incorporated when it formed. Their decay releases heat continuously for billions of years. For a small object, that heat escapes readily and the body cools. For a larger one, the volume producing heat grows faster than the surface area losing it, so the interior stays warm far longer. A planet of several Earth masses would retain substantial internal heat over the age of the solar system, entirely independent of the sun. It would also retain heat left over from its formation, the gravitational energy released as it assembled, which for a large body takes billions of years to radiate away. Which means a distant planet would likely have a warm interior, possibly a liquid layer, and plausibly some form of internal activity, despite a surface temperature near absolute zero. It would also be radiating that heat faintly in the infrared, which is one of the reasons infrared searches were considered promising, and why an object of that size might be marginally detectable by its own emission, rather than only by reflected sunlight. A pleasant question, and the answer is probably. Nearly every substantial body in the solar system has companions. All 4 giant planets have extensive moon systems. Pluto has 5. A large fraction of Kuiper belt objects are binaries. Moons form in several ways, from a disk of material around the forming planet, from collisions and by capture. If the proposed planet formed among the giant planets and was then scattered outward, it might have carried moons with it, though a violent scattering encounter could also have stripped them. If it formed further out, it would likely have accreted its own small system, and if it were captured from interstellar space, it might have brought companions from its original system. Detecting them would be difficult, but not impossible. Once a planet is found and studied, a moon would reveal itself, either by direct imaging with a large telescope, or by its gravitational effect, and a moon's orbit is the most precise way to measure a planet's mass. So if the object is ever found, one of the early questions would be whether anything is going round it, and the answer would tell us a great deal about where it came from. There's a variant of the formation story worth a chapter, because it's a nice piece of reasoning. Simulations of the early solar system's instability, the period when the giant planets migrated and the system rearranged, often work better if there was an additional ice giant present. With 4 giant planets, the models struggle to reproduce the current architecture without disrupting the inner planets. With 5, the extra 1 absorbs the instability. It's flung out during the chaos, and the remaining 4 settle into something resembling what we observe. So the standard picture, in several versions, includes a 5th giant planet that was ejected, typically thrown out of the solar system entirely by an encounter with Jupiter. Which raises an obvious thought. If a planet was ejected, might it not have been ejected all the way? Might it have been left on a distant bound orbit instead? That's a real possibility in the simulations, though it requires the ejection to be interrupted, usually by a passing star, or by the gravitational influence of the birth cluster's remaining gas. So one version of tonight's story is that the proposed planet is that lost 5th giant, thrown outward 4.5 billion years ago and caught before it could leave, which would make it a survivor of the event that shaped everything else. Let's look outward for a chapter, because other systems tell us whether distant planets are reasonable. Most exoplanets have been found close to their stars, because the detection methods favor that. A planet transiting its star or tugging it measurably, has to be nearby and fast. But a small number have been found at wide separations by direct imaging, photographing the planet itself, separated from the glare of its star. That works only for young systems, where the planets are still hot from formation and glow in the infrared, and only for massive planets far from their stars. Several such systems are known. One has 4 giant planets at separations from about 15 to 70 astronomical units, all imaged directly. The first multi-planet system ever photographed. Others have single companions at even wider separations, out to hundreds of astronomical units, which are difficult to explain by ordinary formation and probably require scattering or capture. So wide-orbit planets exist. They're rare among the systems we can survey, but the surveys are strongly biased against finding them, and the true frequency is poorly known. Which means a planet at several hundred astronomical units is not something unprecedented. It's something we know occurs, at a rate nobody can currently pin down. That technique deserves a chapter, because doing it at all is remarkable. The difficulty is contrast. A star outshines a planet beside it by factors of millions to billions, and the two are separated on the sky by a tiny angle. The solutions combine several tricks. Adaptive optics corrects for atmospheric blurring in real time, using a deformable mirror adjusted hundreds of times a second based on a reference star. A coronagraph blocks the starlight itself, using a physical mask or a more sophisticated optical arrangement that suppresses the star's light while letting the surroundings through. And careful image processing removes the residual glare, using the fact that the star's speckle pattern rotates differently from a real companion as the telescope tracks across the sky. With all of that, planets can be imaged at separations of tens of astronomical units around nearby young stars. None of it helps for our own case, unfortunately. A cold planet in our own solar system doesn't have the glare problem. The sun is far away in angle, but it's extremely faint, and the challenge is sensitivity rather than contrast. Still, the same instruments and detectors developed for one problem contribute to the other, which is how observational astronomy usually progresses. A short chapter returning to the more exotic possibility, because it raises an interesting question of definition. If the gravitational evidence held up, and searches definitively excluded a planet of the required brightness, the black hole possibility would move from curiosity to serious consideration. And then there'd be a question of what to call it. It wouldn't be a planet. A planet is a body of a certain kind, and a 5 Earth mass black hole the size of a grapefruit isn't one by any reasonable definition. It would be the nearest black hole by an enormous margin. The nearest known stellar black hole is over 1,000 light-years away, and it would be an extraordinary object to study. It would also, if it were primordial, be a direct sample of the first instance after the beginning, which nothing else is. The probability is low. Capturing a primordial black hole of exactly the right mass into a solar orbit requires a chain of unlikely events, and the mass ranges where such objects can exist have been steadily squeezed. But it's a legitimate hypothesis with a proposed test, and it makes a point worth remembering. The evidence, such as it is, constrains a mass and an orbit. It says nothing about what the mass is made of. Let's take a reflective chapter, because the history here is mostly of absence. Since Neptune in 1846, the solar system has yielded no new planets. Pluto was found in 1930 and reclassified in 2006. Every other discovery has been a smaller body, an asteroid, a moon, a Kuiper belt object. Meanwhile, there have been repeated predictions. Vulcan, Planet X, Nemesis, Tyche, and now this. Everyone so far has come to nothing. That's not a criticism of the people who made them. Each was a reasonable inference from the data available, and several were made by excellent scientists. It's simply that the outer solar system is enormous and mostly empty, and the temptation to populate it is strong, and the evidence for any particular occupant has always been thin. Which is the reason for caution here, and also the reason the current proposal is treated more seriously than its predecessors, because it's been constructed with the failures of the earlier ones in mind. The pattern to notice is that the successful prediction, Neptune, rested on decades of precise positional measurements of a bright object, and the failures rested on small samples, contested datasets, or errors in the baseline. Where the current case falls on that spectrum is exactly what's being argued about. One last practical chapter, because it's a comfortable thing to know. The survey in Chile is beginning its 10-year program. Within the first 2 or 3 years, its catalogue of distant objects should exceed everything found previously. Within about 5 years, the sample should be large enough and uniform enough for the clustering question to be settled statistically, because the selection function will be known rather than reconstructed. And a direct detection, if the object is within reach, could come at any point in that period, or from one of the other searches running in parallel. So the plausible window for an answer is roughly the next decade, with a possibility of much sooner, and a possibility of an ambiguous outcome if the object is at the far end of its orbit. That's an unusually short horizon for a question of this kind. Many open problems in astronomy have no defined path to resolution at all. Here there is one, it's being walked, and the instrument is on the mountain and taking data. Which means that whatever the answer is, most of us will probably live to hear it, and it will arrive quietly, in a paper, after a long period of careful checking, as these things do. One more thought before the recap, and it's a restful one. If you go outside tonight and look up, you'll see the same sky your grandparents saw, and their grandparents, and everyone before them, for as far back as records go. The constellations shift over tens of thousands of years, but within a life they're fixed. The planets move slowly and predictably along their familiar paths. And whatever is or isn't out beyond Neptune makes no difference to any of it. If a planet of 6 Earth masses is sitting at 500 astronomical units, it has been sitting there for 4.5 billion years, and the sky looks exactly the same as it would if it weren't. That's the strange character of this question. It concerns something that, by construction, has no observable effect on anything except the orbits of a few dozen faint objects that nobody knew existed 30 years ago. Which makes it a very safe thing to wonder about at this hour. Nothing hinges on it. No preparation is possible or required. It's simply a fact about the world that is currently unknown, and will probably become known. And in the meantime, the sky above your roof is precisely as it has always been, and will be tomorrow. A last reflective chapter, because there's a larger thing underneath. The specific question is whether a particular object exists, but the broader one is how well we know our own neighborhood, and the answer is less well than the diagrams suggest. We have surveyed the inner solar system thoroughly. We have mapped the Kuiper belt partially. Beyond that, our knowledge thins rapidly, and past a few hundred astronomical units, it becomes essentially nothing. That's not a failure. It's a consequence of distance and faintness, and the fourth power fall-off in brightness, and of the fact that systematic deep surveys of the whole sky have only become possible very recently. So the honest picture of the solar system is a well-mapped center, a partially explored middle, and an enormous dark periphery about which we can say very little. The Planet 9 question is one specific probe of that periphery, whether or not the planet exists. Asking has driven the surveys that are filling it in. And in 20 years, whatever the answer, we will know that region far better than we do tonight, which is, in the end, more valuable than any single object. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began with the classroom diagram, the Sun, the planets, Neptune at the edge of the page, and with the fact that the page stops far too early. Neptune is 30 astronomical units out. The Sun's gravitational domain reaches perhaps 150,000. If that realm were a football pitch, everything on the diagram would fit in a circle a few millimeters across at the center spot. In all that room, something several times the Earth's mass could sit quietly and go unnoticed, too faint for most surveys, and moving so slowly across the sky that it would look like a fixed star. Then Sedna, found in 2003, a reddish object on an 11,000-year orbit, whose closest approach to the Sun is 76 astronomical units, far too distant for Neptune to have placed it there. Detached, decoupled, unexplained. Then a second such object in 2014, and with it the observation that the most distant known bodies seem to have their orbits oriented similarly, which shouldn't happen. Then 2 astronomers at Caltech who set out to disprove it, and found instead that a planet of several Earth masses on a long elongated orbit would produce exactly that pattern, and, without being asked to, would also produce the perpendicular orbits, the detached objects, and the Sun's 6-degree tilt. And then a decade of looking and not finding. Infrared surveys ruled out anything as large as Saturn. Deep optical searches have covered most of the plausible sky. Volunteers have examined images by hand. Nothing has turned up that fits. Meanwhile, the objection sharpened. The clustering was found in a handful of objects, discovered by different surveys pointed at different parts of the sky at different times. And surveys don't cover the sky evenly. A carefully characterized survey from Hawaii analyzed its own sample, with its biases fully known, and concluded the orientations were consistent with random. The argument has continued since, productively and without resolution, because it turns on how well a small sample selection effects can be reconstructed after the fact. And there are alternatives. A massive disk of small bodies rather than one planet, a modification to gravity at very low accelerations, a primordial black hole the size of a grapefruit, and the possibility that a passing star 4.5 billion years ago, while the Sun was still in its birth cluster, lifted those orbits and then departed, leaving a fossil rather than resident. We've been here before. Neptune was found by calculating where an unseen mass must be, and it was there. Vulcan was found the same way, and it wasn't. The anomaly was real, and the answer was Einstein. Lowell's Planet X was predicted from residuals that turned out not to exist, and Pluto was found in roughly the right place by coincidence. So the field waits. A new observatory in Chile, with the largest camera ever built for astronomy, is beginning a 10-year survey of the whole southern sky, which should either find the object or make the statistics unambiguous. Either way, within a decade or two, the answer arrives. Let me leave you with some things to rest your attention on, not to learn, just quiet facts, true right now, while you lie still. About 80 astronomical units away, more than twice Neptune's distance, a reddish body, 1,000 kilometers across, is falling slowly inward, approaching the closest point of an 11,000-year orbit. The last time it was here, people were beginning to farm. Somewhere between 160 and 200 astronomical units out, 2 spacecraft launched in the 1970s are drifting outward in silence, their power fading, having crossed the boundary of the Sun's magnetic bubble and still nowhere near leaving its gravity. Beyond all of it, in a shell reaching perhaps 100,000 astronomical units in every direction, trillions of icy bodies are moving so slowly that a single orbit takes millions of years. None has ever been directly seen. On a mountain in Chile, a camera the size of a small car and holding 3 billion pixels is photographing the southern sky, thousands of square degrees a night, 20 terabytes before morning, and it will do the same tomorrow and the night after for 10 years. And somewhere in all that dark, cold room, there may or may not be a world several times the size of ours, going round the Sun once every 15,000 years, having done so quietly since before the Earth had oceans. So here's where we stop. The honest answer to tonight's question is, possibly. There's a pattern in the orbits of a few dozen very distant objects that might be real, or might be an artifact of where telescopes happen to point. If it's real, an ordinary planet of a few Earth masses would explain it, along with several other puzzles. Nobody has found it, and a survey now beginning should settle the matter within a decade or two. That's an unusually satisfying kind of open question, well posed, actively pursued, with a defined path to an answer, and both sides agreeing on what would settle it. And nothing about it requires anything from you. Whatever is or isn't out there has been out there since long before the Earth had oceans. and will still be there in the morning, unchanged. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. The room beyond Neptune is very large, and very dark, and very cold, and extremely quiet. Nothing there is in a hurry. Nothing there has ever been in a hurry. And the map on the classroom wall was never the whole house, only the first few rooms, well lit, with the doors standing open onto a great deal of darkness that nobody has finished exploring. Sleep well.